Okay, last example of exponential decay. Living tissue contains two isotopes of carbon, carbon-14, which is radioactive, and carbon-12, which is stable. The ratio of these is constant while the tissue is alive. When the tissue dies, the carbon-12 remains, but the carbon-14 decays, with a half-life of approximately 5,715 years. What is the age of a fossil in which the carbon-14 has decayed to 20% of its original amount? So if you've heard of carbon dating, this is a technique that is commonly used to estimate the age of things like fossils, relics, things that were originally made out of wood or cloth, or basically anything that's really old but was once part of a living plant or animal. Something that's made out of material that was once part of a living plant or animal. They can use this technique to estimate how many years it's been since that material was actually alive, based on the ratio of these two carbon isotopes and how much of the radioactive carbon-14 is still present. So to solve this particular problem, it's asking what is the age of a fossil in which the carbon-14 has decayed to 20% of its original amount. So we're talking about exponential decay, which means that the formula for the amount of, in this case, carbon-14 remaining after t number of years looks like this. It's equal to the original amount, the initial amount that we started with at time t equals 0, which in this case would be when the fossil was a living creature. It's equal to a sub 0 times e to the kt. So the k is the natural log of 1/2 divided by the half-life. And for carbon-14, that's about 5,715 years. So the formula for how much carbon-14 remains t years after it was originally alive is a sub 0, the initial amount, times e to the kt, where k is ln of 1/2 divided by 5,715, and t is the number of years. That's what we're trying to find, the age of the fossil. So for that k, we want to know when is a sub 0 times e to that k times t equal to 20% of the original amount. Remember, the original amount was a sub 0. 20% of that original amount would be 0.20 times a sub 0. So the equation we have to solve is a sub 0 times e to the ln of 1/2 divided by 5,715 times t equals 0.20 times a sub 0, 20% of a sub 0. So we got to take that equation and solve it for t. First thing we do is divide both sides by the number a sub 0. So it just cancels out on both sides. It doesn't matter what that number was, because it divides out on both sides, and now we have the equation e to the kt equals 0.20. Now, how do we get that e out of the way? By now we know we undo the e with ln, take the natural logarithm of both sides, and we get kt equals the ln of 0.20. Now remember, we're trying to solve for t, so to go from k times t to just t, divide both sides by k. So t equals the natural log of 0.20 divided by this number here. So now we're essentially done solving. We just have to put this into the calculator. So pause the video, calculate this on your own calculator, make sure the answer you get matches what I get. Okay, did you do that? Did you unpause? Let me show you now what I get when I put this into my calculator. So I'm putting it in as the ln of 0.20 divided by, so the number k, I'm going to put in as parenthesis ln of 1/2 divided by 5715, close parentheses, equals 13269.8 something. So if you got something different, take a look at how I put that in, where I put my parentheses and so forth. So that was the ln of 0.20 divided by, in parentheses, the ln of 1/2, 1 divided by 2, over 5,715. So T turned out to be 13,270 when I round it to the nearest number of years. 13270, 13,270 years. If it was 50% of the original amount, that would be 1 half-life exactly, 5,715 years. After 2 half-lives, so 2 times that number of years, we'd be down to 25% of the original amount, half of the original amount. And then it's a little bit more time after that that takes before we're down to 20%. 2 half-lives and then a little bit more time after that. So 13,270 years. Now, before I end, let me give you a hint for one of the homework problems. Number 33, the number of bacteria in a culture is increasing according to the law of exponential growth. After 3 years, there are 100 bacteria, and after hours, it's growing by the hour. After 3 hours, there are 100 bacteria, and after 5 hours, there are 400 bacteria. How many bacteria will there be after 6 hours? Now, there are several different ways you could go about solving this. Some easier, some harder. You can set this up using an exponential growth model with that kind of equation, work out what all the numbers are. But the easiest way to solve this is to think about, well, not half-lives because we're talking about growth, but maybe a doubling life. How long does it take for the number of bacteria to double? How many hours for the bacteria to double? And if you can answer that question, then it's not very much more work to answer the question of how many bacteria there will be after 6 hours. So think about that. How many hours does it take before the number of bacteria reaches twice as much as it was before? So with that hint, that becomes a fairly easy question to answer, and so I will just leave it at that.